Scuba diver, breathe like fire, fluid mechanics project at Technion.
In this project, we built a miniature diver which we named Octopus, containing a trapped air bubble. By changing the pressure inside a sealed bottle using a syringe, we measured how the bubble volume changed and how that affected the diver's buoyancy. Our setup included Octopus, who weighed in at 6 grams with a solid volume of about 6.4 milliliters, and our bottle, which held 525 milliliters of liquid.
The diver sinks in when its average density becomes greater than the water's density. This happens because we add pressure to the bottle using the syringe, which condenses the air bubble, raising the density of the octopus. Octopus in tap water, the density of the water is 1000 kilograms per meter cube, so the required volume is 6 milliliters. Octopus's actual volume was 6.4 milliliters, so naturally it floats. To make it sink, we need to compress the air bubble so that the total volume dropped from 6.4 milliliters to around 6 milliliters. The ideal gas law at constant temperature says PV is constant, so increasing the pressure inside the bottle reduces the bubble volume.
In tap water, injecting about 2.5 milliliters of air into the bottle increased the pressure enough to shrink the bubble from around 0.4 milliliters down closer to 0, reducing the diver's total volume to the required 6.0 milliliters. As predicted, the diver sank at that point.
Next, we repeated the experiment with salt water to model ocean water. The mass of the liquid increased from 525 grams to 620 grams, so the saltwater density was approximately 1180 kilograms per meter cube, which is significantly denser than tap water. We injected 5 milliliters of air, which raised the pressure, but it was still not enough to shrink the bubble by over a millimeter and reach its neutral buoyancy. As predicted by the higher density, Octopus did not sink. Only when we squeezed the bottle very hard by hand, creating a much larger pressure increase, did Octopus finally sink, again matching the theoretical requirement of a much smaller volume.
We were curious as to what would happen if we used diet soda. Hence, we performed this experiment, and as a result, Octopus showed no noticeable movement even under significant squeezing of the bottle. This happened because the soda is carbonated and highly pressurized, meaning the liquid already contains dissolved carbon dioxide that increases its internal pressure. As a result, when we tried to compress the bottle, the pressure change transmitted to the diver was much smaller than expected, so the air bubble inside the diver barely compressed and its buoyancy stayed almost constant. Although we didn't test it, if the water temperature were raised, Octopus would become more buoyant. According to the ideal gas law, warming the water increases the temperature of the trapped air bubble, causing it to expand and increase Octopus's total volume.
Fluid mechanics project at Technion.